Today we're going to take a look at section 2.3, at least the first half of it. We're going to be taking a look at other set operations in this section. In particular, we've seen some of these ideas before in different ways, but not exactly in the way presented in this section. So for starters, set theory operations offer powerful ways to model relationships, distinctions, and connections within groups. They reflect a deeper truth about the order and relationships embodied in God's creation. Exploring these ideas reminds us that God is a God of unity and distinction, designing systems that are both logical and interconnected. Recognizing this enriches our teaching and deepens our appreciation for the structure and the meaning behind foundation mathematical concepts. Let's pray. Dear Heavenly Father, I thank you for another day to be here, to be at OBU, to be learning and to be growing and preparing for the future that you have laid out for us. I pray that you would help the students as we're working today, that the details that we're working through would be clear and concise, and that as we move into group work, that would be productive time as well. We pray in Jesus' name. Amen. All right, so we're going to take a look at a couple of set operations to start with. I know we're going to get through these first two at least today. The first one is called set intersection. So a set intersection is the set of all elements that are common to both sets or to two sets. And we're going to write down what that looks like in set builder notation. It's not our favorite notation, but we are going to manage just fine. Notationally, an intersection looks like an upside down U. You can kind of also look at it and think about it as looking kind of like the letter N for intersection without the stick on the left. That's one of the options. And as we look at the intersection, what we're describing is this is the set of all things, set of all X, such that X is an element of A and X is an element of B. Okay, so when you think of set intersection, I want you to think of just the word intersection. You can think of it in terms of driving, like the intersection of two streets. You can think of it in terms of like algebra or geometry where lines intersect. Intersection is the crossing space, right? It's what they share in common. It means the exact same thing as intersection that you've used in those other contexts. Intersection. The other one in this piece, these two in a row, is union. So a set union is the set of all objects in one set or the other or both. And the union notation actually looks like a U, so that's friendly. And again, notationally, this is the set of all X such that X is an element of A or X is an element of B. And what I'd like you to notice first is that while what is underlined says one set or the other or both, you don't see the word both represented here the way I've written it in set builder notation. The reason is because in mathematics we use what's called an inclusive or, which means you get the both part sort of for free. Okay, so it isn't necessary to write it there. But you need to remember that or both is an option. So if both things are happening, it's still included. Okay, this is a union. And when you think of union, I want you to think of a wedding. Okay, we call that a union when you get married, right? It's the same union that they're talking about here. What it's supposed to mean from a biblical perspective is that now you're a part of each other's lives and all of you is all of them. So if you come into this relationship with debt, they now have debt. And if they come into the relationship with children, now you have children. You get it all. You can also think of it like the family picture, right? So imagine you have like a blended family situation and you want a family picture of all your kids. Well, you get his kids, you get your kids, and you get the kids you share all together, right? It's the family picture. It's the picture of everything. That's what a union is. Now, we had taken a look at Venn diagrams last time, correct? We had done a little bit of that. Not a lot, but a little bit, I think, yeah? So let me draw a picture for each one of these in terms of Venn diagrams as well. So a set intersection, I'll do this on the top left, is like this. So this is our Venn diagram. It's got two sets. Our sets are A and B. Oops, hang on just a second. That didn't do what I wanted it to do. Let me try that again. So here's A and here's B inside of the universal set. And The intersection is this piece in the middle that's inside of both of the circles at the same time. That's the image for a set intersection. And for a set union, start out with the same basic picture, the same overlapping sets. We have our same A and our B and our universal set on the outside. And the union means that you get the entire group of A and the entire group of B. Okay, so you get the overlap in the middle, that's the or both part, but you get the outer part of A and the outer part of B. You might notice that if you were to have shaded them like each in their own color, you would have double shaded the part in the middle. We're going to come back to that idea in a little bit. We don't double it up, right? Like the children we share in common are not supposed to be like better than the children that are each individual category. That'd be weird, right? So we're not double shading that in the sense that it double counts things, and we'll discuss that a little bit more in a little bit. Okay, so we're actually going to look at one more, relative difference. So relative difference is the set of all elements in one set that are not in the other. This is a very nice word, difference, because we think difference means subtraction a lot of times anyway. So we use the subtraction symbol. And it looks like this. This is the set of elements of X such that X is in A and X is not in B. So it's included in one set, but it's not in the other set. And what you can think about in terms of a picture point of view from context point is a prenup. So a prenuptial agreement is usually one of these things where one of the people, like if you're entering into it in a wise way, typically one person has a lot more assets than the other one, right? So there's some sort of sense that maybe their family doesn't want you marrying them for your money. You know what I'm talking about, right? Okay, so there was a movie a while back. It's been a long time. And it's not entirely appropriate. But it had George Clooney in it. And I think, I can't remember the co-star, but they went back and forth the entire movie of one person having a prenup and then the other one didn't. And I don't remember what it was called even. It was all about prenups, okay? This is a terrible idea as a general statement, right? But that's what it is it's the idea that if we get divorced, we each leave with what we brought in. Okay, and it's usually terms of finances, that's the idea, okay? So in terms of a picture, it looks like this. So draw yourself a Venn diagram again, same as before, overlapping two circles. Oops. And we have A and B and the union. And this is the part that's in A and it's not in B, which means it's this outer sort of moon-shaped part over here. Okay, it's this space. It is in A, but it is excluded from B, so it doesn't get the overlap of B. Notice we don't throw extra stuff in from B, right? That's not thrown in, okay? It's just the stuff in this outer part of A. Okay, does that make sense? Okay, so we're gonna do an example. We're gonna take a look at a blended family situation because it does lend itself well to these ideas. It works really nicely. So we're gonna consider Mary, single mom to one child, Mark, and Joe, single dad to two children, Jack and Jill. Mary and Joe get married. And together they have two children, Ann and Andy. If M is equal to Mary's kids and J is equal to Joe's kids, and let's just think biological, not in terms of, wait a minute, they're all their kids. I understand that. I understand that more than most, right? Like I get it. But just think biological when we're talking about that, okay? So M is Mary's biological kids, J is Joe's biological kids. Find and describe the following. So what would it mean for us to talk about the intersection of M and J? What would that mean? Like, as in, what does this symbol mean? Let me clarify that. What was this symbol?
The set intersection.
It's intersection. All right, it's intersection. What is an intersection?
The middle.
The middle of the picture. The phrase that I'm looking for is the phrase what they have in common. It's what they share.
Common to both.
Okay, common to both. Yes, common to both. So which of these groupings of children, there's several children listed, are common to both Mary and Joe? Ann and Andy. So this is Ann and Andy. And we're using sets, so we'll put them in those curly braces. Okay, so what would this symbol mean right here? What's that mean?
It's
It's a union. And what does union mean?
one set or the other.
One set or the other or both. You get the entire gamut of all the children, right? So who's going to get listed in these curly braces? Jack and Jill. Who else? Anne and Andy. And one more. Mark. Okay? It's the family picture. You get everybody. Okay, in this case, we're talking children, not the parents too, but you get all of the children. Okay, so what would it mean if I do this symbol here, this sort of subtraction looking symbol? What's that symbol actually represent? What was it called? Relative difference. So difference, just like with addition and subtraction of numbers, means I'm taking something away. Okay, so what am I starting with? Mary's kids. And I'm taking away who? Joe's kids. Okay, so any child that Joe has cannot be in my curly braces. Y'all with me? Only the ones that Mary alone has. So who would that be in this particular description? Mark. He is the only one that would be in that set. Simply Mark. It's Mary's kids only. Okay? If you drew them in a picture, you could actually set this up in a picture very nicely as well. Let me set it up in a picture for us just so that you have another visual of this. If we did all our picture stuff right here. So as we're putting these in, we're going to put the people's, so I'm going to put their names. So this is Mary. Okay, forgot to change that. Let's try it one more time. This is Mary, and this is Joe. Those are the adults. They get married. Mary brings into the marriage Mark, not Mac. Let's try again. Mark, and Joe brings in, is it Jack and Jill? Jack and Jill, and then combined together they have Anne and Andy. Right? So Anne and Andy are the ones that they have together. Mark came in with Mary. Jack and Jill came in with Joe. This would be the picture perspective of where each of those children sort of resided. Okay, is that all right? Okay. We can actually talk about some set operations, things that are true about sets like these. In particular, you'll see some words that you've seen used in algebra kind of stuff before. Commutative, associative, and distributive. And there are properties that exist for real numbers that we work with, but they also exist for sets. So let me explain what these look like. So this first one says it's the commutativity of set intersection and union. So for all sets, A and B, A intersection with B is the same as the B intersecting with A. And A union of B is the same as B union of A. So commutativity literally means order doesn't matter. We get it in addition, right? 3 plus 5 is 5 plus 3, right? So if children are learning their addition tables, and multiplication works this way too, and they learn all the facts for the ones, 1 plus something, 1 plus something, all the 1 pluses, right? And they do that with the 2s, and they do that with the 3s. By the time they get to the 9s, there's very little more that they need to actually learn because they already learned plus 9 with each of the other values. Okay, so commutativity means that the order doesn't matter. It also has to do, you hear that same word commute when you talk about going to and from like work and home. You've probably heard commute, how long is your commute? My commute's 22 minutes from my house unless they've got I-40 with construction, in which case you just never know, okay? But it's supposed to be 22 minutes, right? Commute just means I'm changing locations, right? So I wouldn't say that it's any longer to go home than it is to come here. It's 22 minutes both ways. The direction doesn't matter in theory, traffic aside and so forth, okay? Now associativity property, the associative property or the associativity set of set intersections and set unions, it's the same for all sets A and B, okay? So that part's the same. We need to throw in C, so A, B, and C this time. And it looks like this. It says A intersect B intersect C is the same as A intersect B and then intersect C. Pay attention to where the parentheses are. That's the whole difference. And we can do the same thing with union. A union, B union C is the same as A union B and then union C. Associative. You use this word. I was talking to one of my teenagers about this the other day. The word associative, because they were doing some algebra stuff with these properties. Associative is who you associate with. It's the same thing here. Who's associated or what set's associated with what set? Well, the way that we represent this for sets, just like we do for numbers when we're working in algebra, is we do parentheses. That shows us the association. It's who you're grouped together with. So what this is telling you is that the grouping order doesn't matter. So first I group B and C together and then throw A in. It's the same group when I'm all said and done, or it's the same elements as if I had grouped A and B together first and thrown in C. Okay? And again, this is exactly what happens if you have friendships as well. So let's say that Kira and Anna are really good friends, and then they throw Emma in the mix, right? It doesn't matter if Emma and Anna were friends first and then Kira, right? They're all now grouped together. They're all friends. It doesn't matter the order in which it started. You become a group together, okay? That's what's happening here as well. You have the same groupings when you're done. So this is associativity. And then the last one, I think it's on the next page for you probably as well, is distribution of sets. Now, distribution always involves more than one operation. So when we do it in algebra, it means that we're taking something with multiplication and we're throwing it over on top of some kind of a grouping of addition or some kind of a grouping of subtraction. So we get two kind of different operations in the mix. Same thing's going to happen here. This is going to be a way in which we can combine unions and intersections into the same statement. And so again, it's got the same for all sets A and B and C, all that again. And it says the following. So we've got one statement. So A intersect B union C. So if you have the union of B and C and then you intersect it with A, this actually means that you are going to intersect A with B and you're going to intersect A with C, and then you're going to be doing the union of that intersection. And it kind of, again, feels like what we do with algebra. If I were to take this A intersect part at the beginning, and I were going to distribute, it through like so, this A intersect would apply to B, which it does. This A intersect would apply to C, which it does. And the union that was in between the B and C to begin with stays union. Okay? The reason we don't see it look quite like this with multiplication is because we usually don't use multiplication symbols, like a multiplication dot where this intersection is, or the X, right? We usually just use the fact that they're right beside each other to represent they're being multiplied. But it's the same process. Okay, is that all right? Makes sense? More than anything, at least the first two, right? The commutative and associative, it's everything that you would expect to be true. Nothing weird's going on is what they're telling you, okay? Nothing weird's going on. It's not happening in a counterintuitive way. All right, one more, and then we're gonna do some examples. Two more things, and we're gonna do some examples. So the first one is cardinal number formula, and I already alluded to this a little bit, and so I'm gonna bring us back to a picture here in a moment. But this actually talks about, remember, cardinal means counting, how many? Okay, so this is a counting argument. It talks about the number of items in a union. So if you're looking for the number of items in the union of A and B, the way that this works is that you add the number of items in set A to the number of items in set B, and then you subtract the number of items in an intersection. The initial layout of this probably should feel a little counterintuitive because our definition of union said it's in one set or the other set or both. And it kind of looks like this mirrors that definition. I'm in one set A, I'm in the other set B, but then I'm somehow subtracting off the both part. That's what it looks like, right? Are y'all with me? Okay, so let's draw the picture that we saw for union before and talk about why this is actually not what's happening here. Okay, so we've got our sets A, B, and the universal set. And the first thing I'm going to do is I'm going to sort of just follow from left to right what this says on the right-hand side of the equation. Like I'm going to start here, okay? I'm going to start at the number of items in A. So if I were to look at the number of items in set A, and you think about the Joe and Mary example if you wish, I would be looking at the entire circle A, right? All the people or elements or whatever's in it. And it would look like if shaded all of this in purple. Okay, this part that I've shaded is the number of items in A. Okay, so I'm going to choose an equally annoying color. We're going to use red. The red and they don't show up very well in these dark backgrounds, but it's going to be okay. So we're going to do the number of items in B now. Okay, so if I do the number of items in B, it's all of this in set B. Okay, pretty good so far. So I've counted everything that's purple, I've counted everything that's red, and what happened in the middle? What was that?
It's double shaded.
It's double shaded. And for the purposes of counting, it means we double counted it. You with me? It got shaded twice. So the reason that you're seeing us take it out here is because I'm removing the double counting. Okay, so that's what this does, is it removes the double counting. We're going to see examples of these things. We're just establishing what they are first, so bear with me on that, okay? There's only one more thing we're establishing before we start something like actually doing a problem. You ready for it? You're like, yes, please, let's get that last thing underway. The last one is Cartesian product. The Cartesian product is the set of all ordered pairs such that the first component comes from the first set and the second component comes from the second set. And by way of explaining this, I'm going to show you an example. The concept itself is not terribly difficult, but it shows itself really nicely in an example, better than it does if I just explain it in words. So we're going to take an example. I didn't want blue. Let's try that again. Example. And we're going to let set A be the letters X, Y, and Z. And we're going to let set B be something distinguishably different, just the numbers 1 and 2. Okay? Because I don't want you to confuse where things came from. Now, let me give you this example with the numbers and the letters, and then I'll give you like a verbal description of something in real life that connects to this idea too, okay? Okay, so what we're doing is we're doing pairings of things, and we're going to list all the pairings. But the condition is that one of the paired items has to come from set A, and the other paired that it's paired with has to come from set B. In other words, I can't pair X and Y together. Are you with me? Because they're both in set A. So I take an element from set A, say X, and I pair it with an element in set B, say 1. So one possible pairing is X1. Another possible pairing would have been X2. Those are all the options that X can be paired up with, correct? Okay. But I also have the pairing Y with 1, or Y with 2, or Z with 1, and Z with 2. And all of this is inside of curly braces. This is a collection, right, or a set of ordered pairs. Now, it's the same kind of ordered pairs that are in the Cartesian plane, right? When you do algebra and geometry and you have like a point in XY ordered pair like that, that's an ordered pairing that works like this. It's not any different. Like, I don't pair X with another X. It doesn't work like that in the XY plane. I can't get a location that way, right? I do a left-right distance, that's an X distance, and I do an up-down distance, that's my Y distance. X must go with Y, otherwise I don't have an ordered pair in the plane. That's an example of this. Another example I think I've talked to you about my mom's friend Tina when we were growing up. She had 3 kids, and my mom had 3 kids, and we'd all want to get together and we'd play. But I'm telling you what, I did not want to play with my sister and my brother. Shocker, right? Who did I want to play with? Well, somebody else in that other household that I didn't see all the time, right? It didn't even always matter which one of them. It was just somebody else. So there's this question of how these pairings were going to work. Well, this would have been a collection of all the possible pairings if we paired each one of the people in my household, children, up with each one of the people in her household. Is that right? Okay. I think we have time for the first two examples here, and then we'll push pause. So, example number 2 actually talks about shading sets. So, the first thing you need to know is that this is going to be Venn diagram pictures, and however many sets are listed tells you how many circles you're going to draw. So on A, how many circles am I going to draw? It's not a trick question, I promise. 2, thank you. And on B, I'm going to draw 3. Okay, everybody good so far? The letters that are listed tell you how many circles you're going to draw. All right, so the first one has 2 circles to draw, and those circles are A and B with the universal set here outside. Always looks like this. Now, this particular example, you could probably reason your way through and figure out what you're going to shade without doing what I'm about to do. I understand that. Okay, so what I'm about to show you is a little overkill for this example. But the idea of reasoning through it when you get to 3 sets is much more complicated, okay? And when we get to that 3 sets, we want to have something established that's going to work on everything. So I'm going to start with this one with 2 sets so that you can see how it works. Are you willing to work with me on that? Okay. So what we're going to do is we're going to recognize that there's different spaces in this diagram, right? And we talked about them before, like with Mary and Joe. There's this outer space of A. There's the overlapping space in the middle. There's this outer space of B. And then there's this outer part of the rectangle that's not inside of the circles at all. Okay? And we're going to number them. You could letter them if you wanted to, but I usually number them with the different regions that I see. And I always number them like this. But again, you can number them however you want. Just don't get too creative or you're going to confuse yourself. Okay? And what we're going to do is we're going to very strategically go through, right, in an organized way, what we see happening here. For example, this says that I have A with the bar on the top. Do you guys remember what that bar on the top means? It's been a minute since we did them. Okay, it means complement. So when you put the bar on top of something, it means things that are not in A. Okay, so whenever the bar is on the top, it means not. You can kind of think of it like negation or opposite of. Okay, so when I'm looking at A with a bar on the top of it, and I'm looking at these 4 numbers, 1, 2, 3, 4, I want to list the numbers that are not in circle A. So Madison says 3. Somebody else have one? There's one more. And Madison says 4. Thank you. We'll give you credit for both of those. Good job. All right, 3 and 4. Does everybody understand where the 3 and 4 came from? It's really important. Okay. Now, the other item over here, the way that the problem is given to us, says B with a bar on the top of it, meaning the same thing. I need to list every number that is not in circle B. What numbers are those? 1 and 4. Very good. Okay, everybody good with that? Fabulous. So these are sort of the individual pieces of this argument here. And then what it says I'm supposed to do is that I'm supposed to join those individual pieces together with some symbol. What does that symbol that's in between them mean? Union. And what did union mean?
Bring it together.
Bring it together, like grouping it all together. You get everything, right? Union means I get everything. So I get the 3 and the 4 because they were listed on set A, complement, and I'm going to also get a 1 and a 4, but I don't need to relist it because they're in B complements. I get everything. And this is the work that then supports the shading that I'm about to do. And the shading that I'm about to do is going to be shading the regions 3, 4, and 1. If it really bothers you, rewrite them in 1, 2, 3. Okay, so I'm going to be shading 3 and 4. And 1. And this shading is what I was actually asked to do, but the work before it was how we're coming to the point of what do we shade. Okay, what do we think? It's okay? Okay, let's try one that has the 3 circles now. So again, how do I know that this has 3 circles?
There's 3.
There's 3 letters, you got it. So I need 3 overlapping circles, or ovals. If you draw ovals, it'll be okay. And we need sets A, B, and C with the universal set out here. And again, this is typically how you see it drawn. There's nothing special about A being on the left and B being on the right and C being below, but you know, this is typical.
Sorry, I actually have a question for the last one.
Sure. What's up?
You said it was union and we didn't say that 2 was a part of it?
Correct.
Because maybe I did it wrong.
So Zion, probably what you're thinking about is the union of A and B. But this particular one's not the union of A and B. It's the union of A complement and B complement. That's why B is the number 2 in the middle is not included. Yeah. Yeah. Good question, good question. Okay, do you guys have 3 circles drawn? Okay, I want you to count how many different locations there are in this diagram. Hint, it's more than 4. How many different sort of regions or spaces is this picture like divided up into now? Imagine you were making a mosaic and you were tiling something. How many do you see? 8 is right. Very good, Madison. 8. So again, typically the way that I will number mine is straight across the top, straight through the middle, and then the bottom and outside. So my numbers will always look like this. 1, 2, 3, 4, 5, 6, 7 down here with C and 8 on the outside. There's nothing special about that. That's just the adaptation that I've used. And again, your book actually does some examples, I believe, that use letters in there too, which is fine. There's nothing wrong with that. Okay, so grouping symbols. Just like with algebra, we work grouping symbols outward. So we start inside with the grouping symbols, and we first see that we've got A and B listed inside. So what numbers do you see inside circle A? 1, 2, 4, and 5. What numbers do you see inside of circle B? 2, 3, 5, and 6. Very good. Does everybody see where those numbers came from? Okay. Inside the parentheses, it says I'm going to join A and B together with the intersection symbol. All right, that's what this symbol is. What does intersection mean? The middle, what they have in common. So what numbers do they have in common, either from the list or from the picture? 2 and 5. So I'm going to list 2 and 5 down here as the intersection from this picture. The next thing is that I'm going to join C with this. What numbers are inside circle C? 4, 5, 6, and 7. And again, I go back to the original problem I was given. It says to take that A intersect B, which we know is 2, 5, and to union it, like how I turned that into a verb, union it with C. What does union mean? Combine. You get everything, right? So you get 2 and 5, because they were already in A intersect B. And then you also get a 4. I don't need to list the 5 again. Then 6 and 7. And I'm going to go back then, I'm going to shade each of these regions in that picture. So I have 2 and 5. And then I have 4, 6, and 7. And the shading part is the answer to the question I was asked.